So today, we're going to take a journey deep inside one of them. I'm really excited to guide you into this incredible world to explore the building blocks of, well, pretty much everything. Everything you can see. Just take a look around the room you're in, the air you're breathing, even the stars way up in the sky. Yep, it's all made of atoms. They are the absolute fundamental building blocks of matter. They're so insanely tiny that you could fit millions of them on the head of a pin. And yet, they build our entire universe. So here's the plan. We're going to start with the basics. What exactly is an atom? Then we'll look at its anatomy piece by piece. After that, we get to the really fun part. What happens when atoms start to change? And to wrap it all up, we'll see how these tiny little particles make a huge difference in our world every day. Okay, let's just dive right in. Part 1, what is an atom? Well, to put it simply, imagine you could take anything, your phone or glass of water, anything, and just keep breaking it down into smaller and smaller pieces. The very last piece you'd end up with, the smallest possible unit, that's an atom. The textbook definition says it's the smallest particle of an element. But, and this is where things get really cool, these unbelievably tiny building blocks are actually made of even smaller things. And these components are the three main characters of our story today: the proton, the neutron, and the electron. These are what we call subatomic particles, and they define absolutely everything about an atom. This little chart here breaks it down perfectly. You can see protons have a positive charge. Neutrons are neutral. That's an easy one to remember. And electrons are negative. But now, look at the mass. Protons and neutrons are about the same size. We'll call it a mass of 1. But the electron, it's so tiny, its mass is almost 0 in comparison. Seriously, it's like comparing a bowling ball to a little speck of dust. And that detail is going to be super important in a bit. So, we've met the particles. Let's move on to part 2 and see how these pieces actually come together to form a whole atom. Right at the very heart of the atom, we find the nucleus. Just picture this super dense, heavy little ball where all the positive protons and the neutral neutrons are packed in really tight. And because it's full of all those positive protons, the nucleus itself has an overall positive charge. So, where are the negative electrons? Well, a really great way to picture this whole thing is to think about a solar system. The nucleus is like the sun at the center, and the electrons are like planets, zipping around the nucleus in these specific paths we call shells. They don't just wander off, they have their own designated orbits. Okay, so how can we tell all these different types of atoms apart? The secret is something called the atomic number. It's super simple, it's just the number of protons in the nucleus. And that number is like a unique fingerprint for every single element. If an atom has 6 protons, it is always carbon. If it has 8, it's always oxygen, no exceptions. And here's a cool trick. In a normal, balanced atom, the number of positive protons has to equal the number of negative electrons. So that one little number actually tells you both. The other key number is the mass number. This one's also pretty straightforward. You just add up the number of protons and neutrons. That's it. And remember how we said electrons have basically 0 mass? That's why we don't even bother counting them here. The mass number is pretty much the total mass of the entire atom. And those electrons orbiting the nucleus, they don't just pile in randomly. They have to follow very specific rules. The first shell, the one closest to the center, can only hold 2 electrons, max. Once that's full, they start filling up the second shell, which holds 8, and then the third shell, which also holds 8. This super orderly arrangement, this system of rules, is basically the entire foundation of chemistry. All right, so that's what a perfectly balanced neutral atom looks like. But what happens when that perfect balance gets all messed up? That brings us to part 3, where we're going to meet ions and isotopes. First up, let's talk about the ion. An ion is just an atom that isn't neutral anymore. And why isn't it neutral? Because it's either gained an extra electron or it's lost one. It's that change in the electron count that gives the whole atom an electrical charge. This slide lays it out perfectly. Over on the left, you've got your neutral atom. It's all about balance, right? The number of positive protons is the same as the number of negative electrons, so there's no overall charge. But look at the ion. That balance is gone. The scales have tipped one way or the other, and now you've got an atom with an overall charge. Now, the second type of variation is the isotope. This is a totally different thing. With an isotope, the number of protons stays exactly the same, but the number of neutrons is different. Carbon is the perfect example to understand this. Most of the carbon in the world is carbon-12. It's got 6 protons and 6 neutrons.
But there's a heavier version, an isotope, called carbon-14. Now, it still has 6 protons, so it's still carbon. That's the key. But it's got 8 neutrons instead of 6. Those extra neutrons make its nucleus a little crowded, a little unstable. And that instability is exactly what we mean when we say something is radioactive.
I know, ions and isotopes can sound like really abstract science terms, but trust me, they have some pretty amazing and practical uses all around us. Which brings us to our final section, atoms in our world.
Ever wondered how a neon sign actually glows? It's all about ions. What happens is a bunch of electricity gets zapped through a tube full of neon gas. All that energy knocks electrons off of the neon atoms, which turns them into charged ions. But when those electrons fall back into place, they release that extra energy as a little photon of light. And millions of those photons create that awesome glow. So what about those unstable isotopes, like our friend carbon-14? Well, we have a special name for them. Radioisotopes. Because their nuclei are unstable, they're always trying to settle down by releasing energy and particles. We call that release radiation. And yeah, that can sound scary, but scientists have found some truly incredible ways to put that energy to good use. I mean, the applications are just mind-blowing. Think about it. We use them to look into the deep past, with carbon-14 dating ancient remains and uranium-238 telling us the age of rocks. They keep us safe in our own homes. The Immersidium-241 inside your smoke detector is a radioisotope, and they literally save lives in medicine, with things like technetium-99 being used to find tumors. It's just incredible what these unstable atoms can do for us.
So there you have it. From the simple rules that put them together to the powerful ways they can change, the atom is a whole universe of complexity and wonder. We've seen how its secrets power our world, from glowing signs all the way to our understanding of ancient history. It kind of makes you wonder, doesn't it? What other mysteries are still waiting to be discovered inside?